I I don't see him. Not yet.
Hi, Nana. Good morning.
Hey, good morning, Will. How you doing?
Hi, fine. Yeah, okay. Okay. Hi, Martin. You are here. I can see you now. Are you speaking? Yeah, I can hear you speaking. Can you all hear Martin? Hi, Nana. You can hear me?
No, Martin has a mic issue. I think he's fixing it.
Oh, okay, his face. Okay, all right.
Me now?
Yes.
Oh, you are in now?
I'm calling in using my phone because then there's an issue with the computer audio. All right, which is unfortunate. Oh, I see what the problem is. Okay, let me switch back to.
You should be able to hear me
Okay,
now.
do that. We are waiting. Yeah, we are not going anywhere. So, so if you need to switch to a different computer,
So can you see me?
Yeah, I can see you.
No. Can you see me? Can you hear me though?
Yeah, I can hear you. Other than sometimes there is a break in the communication, but we can. Is everybody fine with the audio? Are you all fine? You can hear him well. Yes, I think I can hear.
Yeah, if
I
you
can
could
hear
let us know in
you.
the chat.
Yeah, I can
Let's
hear you.
see.
Yeah. Okay, so they all said they can hear you. So let me do the introduction, and then if there are any fixes, you can do that.
So it sounds like, I'm
Yeah, go
sorry,
ahead.
go ahead. I was just saying that in the chat, it looks like that, all the audio issues have been resolved.
Okay, all right. Yeah, I think you are much clearer now.
Oh, okay, great.
All
Mhm.
right.
Okay, so what I've
Okay,
done,
so good day, everyone, and welcome back to Varsity Virtual Applied Data Science Training Institute. If today is your first time joining us, this has been going on since February the 11th. This is the fourth module. My name is Dr. Kwejan. I'm a professor at Howard University and then director of this training institute. So today is module 4, and today we are privileged to have Dr. Martin Skaczynski to lead us with cluster analysis. Dr. Skaczynski is a data scientist at NIH Division of Cancer Epidemiology and Genetics. He has a broad scientific background that ranges from molecular biology to epidemiology. He's an expert with Python and R programming. Martin holds an MPH in epidemiology and biostatistical methods for public health and clinical research, and also a certificate in data science from Johns Hopkins University, and then a PhD in tumor biology and a teaching certificate from Georgetown University. He also has an MS in biotechnology from, I don't know if I'm pronouncing this right, Jagiellonian University in Poland, a BA in biology from St. Martin's College in Maryland. So as you can see, he is all around, he is everything. So I'm sure he will answer all your questions, whether in tumor biology or biotechnology or whatever you have. So we are very privileged to have Martin to lead this session today. So show your appreciation and then welcome Martin by waving your hands. Put on your video so we can see your faces as you wave your hands. Okay, Martin, again, thank you so much for coming. It's all yours now.
Okay, great. Thank you so much for the wonderful introduction. I'm very happy to be here. This is a wonderful initiative. Really can only say great things about everything I've seen so far with VADSTI. Okay. All right. So today we're going to be talking about clustering, and I'll start just by saying in my own words what we're doing with clustering. Okay. So with clustering, we're going to have our data. Our data are going to be in a format where we have our variables are going to be columns. Okay. And our rows are going to be observations or examples, right? So let's say we're working with clinical data. We're going to have maybe each row will be a patient, right? It could be a time point in a study. Okay? And then the columns are going to be either attributes of those patients or some kind of measurements that we've taken at a time point, right? So basically it goes observations are the rows, and then the variables or attributes are the columns in our data set, okay? And so what we're doing with clustering is we're putting together observations that are similar into groups or into clusters, okay? How are we doing that? Well, we're doing that based off of the features or the attributes. So the columns are basically giving us these attributes that we say, okay, so how similar are the rows based on the columns? And using those kind of similarities, we're able to put together observations that are the most similar. Okay, so that's kind of a high level view of what clustering is. In the chat, I shared a link. Maybe what I'll do is I'll paste that in again, so you'll have it as the latest link. And what that link looks like is it's going to be a link to the slides. Now, so what I have set up here is that the slides are really, built from the Jupyter Notebook that we have. Okay, so you'll see that this Jupyter Notebook has the same content as the slides. All right, the slides are available on GitHub as an HTML file, but if we want to run the code, we're going to have to run it in the Jupyter Notebook. Okay, so I'm going to open up the slides here and kind of give a quick intro to clustering. And if you want to follow along with your own slides in your own browser, let's see if you've got a second monitor, you can click that link that will take you. I'm actually using that exact same link to show you the slides. All right. Okay. So first up, we've got machine learning. What is machine learning? Okay. So machine learning, we're trying to extract some kind of insight from data. We're trying to learn something from the data, make some kind of observation that will hopefully allow us to enact some kind of positive change, right? So that whatever insights we're drawing from this, they're going to be actionable. Okay. And so what does machine learning involve? So you will have some kind of data set that that the model is going to learn from. Okay. So we're going to have to create that data set. Then the model is going to learn from that data set. And then we're going to be able to use that trained model or that fitted model onto new data. We're not always going to be making predictions. In fact, for what we're going to be doing right now, maybe we won't call them predictions. We're going to call those maybe just the cluster labels. So we're going to assign, or cluster assignments. We're going to assign each observation in our data set. We're going to assign it to a cluster. So it's basically we're going to group them together. Okay? And how that looks is in our data frame, we're going to add on a new column, and that column is going to have the cluster assignments. So each observation, let's say we've got a clinical trial, we're going to have, let's say the first patient is going to be in cluster 3. Second patient in our clinical trial is going to be in cluster 1, right? And so each observation in our data set will get a cluster assignment based on our clustering algorithm. But first of all, talking about machine learning, there are two types of machine learning that we can distinguish. We can break machine learning up into two types. Right? So supervised learning and unsupervised learning. Supervised learning is where we have something that we know we want to predict, like a variable in our data set. So a column in our data set that's going to contain these kind of labels. So our data set already comes with labels, and we want to train our model to predict those labels. That's supervised learning. Unsupervised learning, we don't start off with a column that contains our labels, or otherwise I would call it a target variable. We don't have a target variable. Okay, we're just trying to understand the structure, the underlying structure of the data. Okay, so unsupervised learning, we don't have to go in with a hypothesis or something we want to test or something that we're looking for. We're just dumping data into an algorithm and seeing what comes out. Okay, with supervised learning, we'll have kind of an identified prediction task beforehand. Okay? So these are the two types of machine learning: supervised and unsupervised learning. Okay? With supervised learning, there are two main types: okay? Classification and regression. Okay? So won't be discussing regression at all today, but there will be one part, I think, tomorrow that we'll get to with classification, because we're going to be using classification to try to understand our clustering results better. Okay. All right. So there's a lot of text on the slide. I'm not going to read it, not even going to go into it. But basically, we're going to have, in supervised learning, we're going to have labeled data. So there's going to be a column in our data set that contains those labels. Those are the answers that the supervised learning model will learn from. So basically, it'll learn to map the data to the labels. Okay. All right. And then in the future, it'll be able to take new data and then predict the labels for those new data. Okay. In classification, so that's a type of supervised learning where we've got kind of categorical labels. Okay. So something like, what would be an example? So in classification, we might have, let's say, images of nodules in, let's say, like a lung scan, like a CT scan of the lungs, and we want to classify those nodules as either benign or malignant in terms of cancer. Okay. We might have patients in a clinical trial, and we might want to say, are those patients, are they healthy or do they have a disease? That's also classification. So in both those cases, we've got two categories. Okay? So benign and malignant for cancer, or maybe healthy or diseased, right? Maybe positive, negative is another way to put it, right? So in classification, we're going to have those categories. With regression, we're going to have a continuous label. And so what that means is that it can really be any number. With categorical labels, we have a finite number of options, so it's discrete versus continuous, okay? So quick example for this, for classification, it could be that I'm saying, will it rain tomorrow? Yes or no? So that's binary, right? That's classification. For regression, how many inches of rain will we get tomorrow? Right? That's continuous. We can get 2.5 inches of rain, or 3/4 of an inch of rain. So it's continuous. Okay. So that was supervised learning, but our focus today is actually unsupervised learning. Right? And with unsupervised learning, the main type that we want to talk about is actually clustering. Right? And here I've got a little bit about the difference between classification and clustering. But first, let's talk a little bit about unsupervised learning overall. All right. So in unsupervised learning, maybe we're not really trying to make predictions per se, but we're trying to understand the structure, the hidden structure or latent structure of our data. And our data, doesn't have to have any labels. So there's no column in our data set that's singled out as this is our target variable or our response variable. Okay. So we're treating all of the columns in our data set equally. Okay. All right. And there are different types of unsupervised learning. Okay. Today we'll be talking about clustering, and then tomorrow there's going to be a little bit of dimensionality reduction. Okay. Just to try to understand our clustering results better. Okay. All right. So here we've got classification versus clustering. So what's the difference? Well, classification is supervised and clustering is unsupervised. Okay? So we would use classification when our goal is to predict the label. Okay? So we've got labeled data and we want to predict our label. That's our goal. With clustering, we're more trying to understand our data, and we're looking specifically at what observations are similar enough that we might want to group them together in the same cluster. Okay? And in those clusters, we want those observations that are in a cluster to be more similar to each other than any of the observations outside of the cluster. Okay? All right. So with classification, we're going to have the labeled data. We know how many unique values there are in the labeled data. Okay? So let's say in the previous example, we have benign and malignant, or negative and positive. We know it's binary. We know there are two classes, so we're going to predict between one of those two classes. With clustering, actually, we don't know how many clusters there should be. Okay? There are ways that we can inform our decision of how many clusters to have. Okay? But it's very much more open-ended. So clustering is more like exploration, whereas classification is more targeted to predicting a specific class. And we know what that class is. We know what the unique values are in that class. Clustering is more open-ended. We're exploring the data. We're trying to learn more about the data, specifically about the data structure. Okay? How do the rows in the data relate to each other? All right. Now, so here, this is from scikit-learn. Scikit-learn is a Python library for machine learning. And so what we have here is we have these different kind of areas. So what I've talked about, I've actually talked about most of these. So we're focusing on clustering today. All right. There's also classification and then regression. Quick review, classification and regression, that's supervised machine learning, and clustering and dimensionality reduction are unsupervised machine learning. Okay? Classification, we're predicting a discrete label, so it's like categorical. There are a finite number of options, discrete options, like benign, malignant, negative, positive, and so on. With regression, the label that we're trying to predict is continuous, and it can have any value. It can be really any number, right, when it's continuous. All right. All right. And so clustering, we're trying to group together similar rows. With dimensionality reduction, what we're doing is we're grouping together similar columns. That's the easiest way to explain it. All right. So our columns are going to be our dimensions. That's the number, the dimensionality of a data set is how many columns we have. So let's say we've got 4 columns. We can use dimensionality reduction and then take those 4 columns and reduce the dimensions down to 2 columns just to make it easier to plot it out as a scatter plot on a 2-dimensional 2D plot. Okay. So that's something we're actually going to do probably tomorrow. With dimensionality reduction. Okay? Now, but this flow chart from scikit-learn kind of tells you how to go about what you're trying to do here. And you see here, so predicting a category, if you're predicting a category and you have labeled data, then you go to classification. Right? But next door to classification is clustering. So if we don't have labeled data, then we're going to apply some kind of clustering technique. And the ones that we're going to talk about is mostly k-means, but I also have some information about mean shift available there. And so this is kind of an overview of machine learning using scikit-learn. Okay, so with clustering, we may not have labels, or we may not care about the labels. If we have labels, then probably we would want to remove them. Okay. So clustering is usually performed on unlabeled data, and it can be kind of a preliminary step in our analysis as part of something called exploratory data analysis. So we'll be exploring the data, trying to learn about the data, okay, and also visualize our clustering results to try to understand our data better. Okay. So there are plenty of clustering algorithms, and we won't know maybe beforehand what the best method will be for our particular situation. Okay. But there are some algorithms that are just, or solutions or techniques that are so popular and so common that it's always a good idea to maybe try those first. The one that immediately comes to mind with clustering is k-means. So this k-means algorithm is usually the one that I would try first when clustering, okay? Because it's fast and it's easy to use, and it's a good first choice that we can then try to find maybe another algorithm that will work better for our situation. But k-means is a great kind of default choice. All right. So I have some links here. All right. And because we're on WebEx, I don't think we can have kind of breakout rooms where we can work in groups. But what I wanted to do is to do a little activity here where everyone can open up these links and focus for sure on k-means at first to try to understand what k-means is doing. Okay. And what this is going to be is when you click on this link, I'm going to open it in a new tab. Okay. It's going to ask you some questions. All right. So what I suggest is that we just pick these things called centroids randomly. Okay. And then you can pick a data set. Okay, so this is for you to explore. I'm going to pick example A. All right. And we're first going to decide how many centroids we want. So we'll add a centroid, add another centroid, and then we'll say go. Okay. And then we can update the centroids until there's really no difference. So here in this very simple example, thanks for posting that, William, just in case someone didn't have that slide open. All right. So here I'm in that first one, which is k-means, and already, when I've hit kind of this button enough, you see there's no change. What that means is that the algorithm, the k-means algorithm, has converged. Okay. And you can see what it's done here. I think it's done a pretty good job of splitting this up into two clusters. I could add another centroid, okay, and then eventually it's going to split it up into 3 clusters, where this middle point is going to be in a cluster of its own. Okay, so that's another potential solution. What this shows is that when we're starting with something like this, is we don't know how many clusters there should be. Depends on the situation, right? Here we might say, okay, we want 2 clusters, or we might want 3. So you can pick the initial centroids randomly, but then experiment with different data sets to try to see how the algorithm works. All right. I'm going to go ahead and do maybe now density bars. Okay. Just to show another example. So I'll add a centroid, add another one. I'm going to do 3, and then I'm going to click go, and then continue clicking to update the centroids until they stop moving. So when the centroids stop moving, that means that the algorithm has converged and has kind of arrived at a final answer. Okay. So it might take a little while, but I think this is actually working out pretty well. I don't see them moving at all now. Okay. So what I've done here is I've clustered this into 3 separate clusters. Right. So again, I'll pick the centroids randomly, and then you can pick another example. Okay. This is maybe the last one that I'll do. So I'll pick a certain number of centroids, and these are being assigned randomly, so I don't control this. And then I'll click go, and I'll keep doing update the centroids, okay, until the algorithm converges, and I'm at my final answer. Okay. So when I look at this, I see it, I think it works really well for this type of data, right? Because I've got these pretty distinct clusters, but how did I know how many centroids to pick? How did I know? Well, I'm familiar with this example, and I kind of knew what I wanted it to look like, okay? But again, it'll depend on the data, okay? So this, kind of packed circles data set, I look at this and I think of like a honeycomb, right? Type shape. And then the important thing is that when I'm clicking update centroids, so updating these centers for the clusters, there's no change. The algorithm has converged, and this is essentially my final result. Okay. All right. So what we'll do now is we'll take a break for everyone to kind of explore k-means, right? And then if you want to, you can as well look at dbScan. All right, so here's dbScan. Right, so it's dbScan, density-based spatial clustering of applications with noise. And then the famous example for dbScan is going to be this smiley face. Okay, and this one you don't have to keep clicking. It's just something you can kind of enjoy. You can use the defaults. You don't have to change any of these inputs. Don't worry about that. And then you can just enjoy this algorithm working through this problem of clustering this data set, this smiley face data set. Okay. All right, so I'm going to leave this up. We'll go ahead and take a break. During the break, I'm also going to answer a question that just came up in the chat. Okay. So how do you avoid bias when deciding how many centroids? That's a really great question. So you want to do it objectively. And so what's the way that we can do this objectively? Would be to have some kind of rule going in about how we're going to choose the number of centroids. Okay, so the number of centroids, that determines the number of clusters. Okay, so we'll have to have some kind of a metric for proper clustering, and based off of that metric, we're going to pick, basically the number of clusters that gives us the best result for that metric. Okay, so thanks for that great question. We're going to do that. If not today, maybe it would be towards the end of today. Then we'll do that tomorrow. Okay, talking about methods of how we can choose how many clusters there should be. Okay, great. All right, let's take a break for everyone to work on this. So I'm going to start up a timer, 10-minute timer. And during this time, you can also ask me questions about clustering. But what I'd like everyone to do is to, at these two links, look at k-means and dbScan, and then maybe, you can think about, I don't think we can work in groups, but, maybe you can think about, how did these two algorithms work? What steps do they take? And then do you notice any limitations? Like, so for example, it would be, oh, this algorithm doesn't work great for this data set. Okay. After we come back from this break, I'm going to ask if anyone wants to kind of contribute their thoughts on any of these algorithms. Okay. Right. And so during the break, I'm still going to be here. You can ask me questions. All right, but this is also a time where you can get up, stretch, get some water, do whatever you need, and then also play around with these two visualization tools.
All right, Martin.
Yes.
All right, I just had a quick question about how does clustering handle sort of already normal clustering pattern that may exist? So you might have hospitals or schools already sort of clustered or across different years. Do you include that data, or do you exclude that data and let it sort of identify naturally through the algorithm?
That's such a great question. So you're absolutely right
picking up a partner that
you may have already maybe some kind of like levels in your data, right? So schools, hospitals, for education, you might have actually multiple levels. Let's say you'll have classes or classrooms, and then classrooms are kind of nested within schools. Schools are nested within districts, and so on, right? And so you'll be aware of that. You'll probably have those labels included in your data, but you probably don't want to include those labels in the input data for clustering, because it's pretty much going to be guaranteed that those are going to be used to create the clusters. And so it's pretty much like a given result that you'll have the clustering based off of those levels that you provide, right? So you would want to maybe hold that data, kind of put it to the side, hold it out, right? Do the clustering, and then do this comparison and say, okay, well, do our clusters actually match the levels that we were interested in, right? So, let's say classroom, school, district, or maybe we'll have inside of a hospital, we'll have, I don't know, departments, then the hospital, and then maybe the county, whatever the levels are, we'll be able to compare our clustering results with those labels, right? And so if they match, then we can look and say, well, what are these other features, these other attributes in our data, these other columns, right? How are they kind of structured in a way that our cluster assignments are matching these labels?
Yeah, thank you. That's very helpful.
Okay, great. So, all right, so I'm looking also in the chat. All right. So from last class, there was, the discussion of the elbow method. That's also here, right? Deciding the best K was Prem's class. I've got materials on that as well. So we can revisit those topics about, choosing the right number of clusters. Okay. All right. So we've got 5 more minutes for everyone to explore. If there are any other questions, please feel free to ask.
I have a question as well from Martin or maybe William. I'm sorry to interrupt again.
Yeah, no, it's not an interruption. Please go ahead.
This is a technical question. I'm just trying to run the HTML from the Jupyter notebook. Is there something special I should be doing? Because the code is not running for me.
No, so you're talking about the Jupyter notebook.
Well, I have the HTML slide that you posted. I have that open in the Jupyter notebook.
Oh,
Is that
so
not the right?
so the Jupyter notebook, file is going to be here, right? So you open up cluster.ipynb,
Oh, that's
and
what I was
that's where
looking for. I couldn't find it. Yeah.
that's where
Where's
you
it?
would run the code.
Oh, this is on Codio. I was in GitHub. I'm sorry. I'm in the wrong place.
Yeah. Now,
Gotta find-
if you have it on GitHub, so
I can go
let
get it
me
from
see.
Codio. That's not a problem.
Yeah. Um,
On GitHub, what I did was I downloaded the HTML, then you can open it and the browser will recognize it. If you
Yeah.
already have it set up so that you can clone from GitHub, then you can clone it to your local drive and pick
Yeah.
and drop to Codio.
Yeah, I don't have it set up the way. I can go to Codio and get it. That's fine. Yeah.
Okay, cool.
Let me show you how
That
you
may-
could. Yeah, let me show you how you could do that, because the link that I posted to the slides, that should run in any browser. As long as you've got internet, it should work, right?
Right, I have that
So let me
running.
post
Mhm.
that. Let me post that link again. All right. And then, but if you want the code, here I'm showing this is our GitHub. Okay. And so what you can do is you can download a zip file if you don't have Git set up. If you do have Git set up, you can clone it using git clone. But let's do download zip. It may take a little while to download because it's there's probably a lot here. Okay. And then inside of module 4, you can open up this cluster.slides.html file in your browser.
Got it.
Okay.
Thank you.
You're welcome. All right, so I'm gonna check on the timer. All right, so we're 50 seconds. So hopefully everyone's wrapping up this quick little exercise where we're looking at k-means, clustering, and dbScan using these kind of visualization tools. All right. And in
Hi,
the
Mark.
chat, I can see. Oh yeah, please go ahead. Hi.
I have a question. I just finished, doing most of the clustering. Which
Mhm.
time or when do you know to use the DB scan or the K-means? I mean, is there a specific one that you would choose for purpose or individual, or how would you choose?
Yeah. So both will give us back cluster assignments. So it's going to be a column of cluster labels. Okay. And we would choose one versus the other because they're going to be adapted to certain types of data. Also, there's a very important distinction between the two. All right. But before I kind of give it away, I want to look in what people posted in the chat. All right. So with PCA, you get an abstraction of the original variables aside from using correlation, how to get back to the original data. Okay. And then here there's a comment saying, I'm noting on k-means we are stuck with the number of centroids labels we give. Excellent. Okay. And it'll force categorization into those centroids or labels. So that's the number of centroids is set at the beginning, and then it's enforced. Okay. This emphasizes the importance of selecting the number of centroids accordingly. Okay, so that's great. So that's one very critical aspect about k-means. You have to set the number of clusters ahead of time. What about dbScan? Does someone want to, you can write this either in the chat or just unmute and let me know. How does dbScan compare to k-means in that respect? Do we need to set the number of clusters beforehand with dbScan? So let me run this again. I'm just using the defaults, right? Okay. So with dbScan, there's no clearly observable categorization. Stephanie, could you maybe let me know what you mean by that?
Yeah, I ran the DB scan using the data bars, I think was the one that I did, some random points. And had I used k-means, I would have visualized and assumed specific categorization, which is not at all what the DB scan produced. So it's a very different product, a very different outcome. If we're using our observation to view a data set, we impose a structure on it that DB scan would likely not give.
Yeah, exactly. And so you hit on the point that exactly what I was looking for. So with dbScan, we don't set the number of clusters beforehand. It's going to be working through the data set and then kind of arrive at that answer for how many clusters there should be. Okay. And for this one, this specific one, the default settings aren't going to be that great. What we would have to do in order to kind of, we'd have to fiddle with the settings in order to get kind of a nice or a better result, right? But this would be an example of a data set where dbScan is not a good choice, right? Or maybe isn't a great choice, right? So we're getting some clusters here. It identified maybe a big cluster in the middle, and then some other clusters out here, and then it didn't even assign clusters to some of these points, right? So with this one, dbScan is not great for that kind of density bars one. Okay, I did this one with, so I did with 3 centroids. I did it with k-means, and it seems to work just, it works okay, right? I mean, maybe it's not great, but it gives us kind of 3 distinct clusters, whereas dbScan kind of fails here, at least with the default settings. All right.
See, and I
But
think that's my question. Yeah. I think that was my question though, because when I just looked at the data, the density bars data set, I would have envisioned the clusters the way k-means did it. We impose a structure on it, right? So
Yeah.
the question that I have left is, where is the error? Are we in error, or is the dbScan, in error? Where is that bias?
Yeah, I think it's coming from dbScan. So dbScan is not the right tool for this data set. Okay, and that k-means is clustering this better, right? But we can try a different example. So for example, the smiley face. Okay, so smiley face is the example where dbScan is the right tool for the job. We just use the default settings. Okay. And it works through, and we don't have to specify how many clusters we want. dbScan basically determines that, right? So what it's going to do, or at least most of the time what it does, is we're going to have 4 clusters. We're going to have the surrounding circle. We're going to have the smile, and then each of the eyes is another cluster, right? So this is an example where dbScan works great. Okay. And it's also an example where k-means maybe doesn't work as well. All right. So if we add a couple centroids, I'm just going to do 3. And this is essentially what k-means clustering results in, is we're just going to split things up into kind of 3 portions. Okay, 3 equal portions. We've got 1/3 is blue, 1/3 is green. The other third is red. Okay, So this is a great illustration of how algorithms are very different. And I would say here, dbScan is doing the right thing, whereas k-means is not able to cluster this correctly. Okay.
This
So
is
one,
where, I'm sorry, this is where machine learning, I think, blows what we've learned statistically manually out of the water, because I think no manual statistical analysis would I assume that data points at the top of a quadrant would cluster with the data points at the bottom of a quadrant, right? That just would not occur, I think, in our standard manual statistical analysis. So, it's kind of blowing my mind that we have to totally rethink what gets clustered under machine learning.
that's such a great point. And you're absolutely right that these machine learning techniques, they're very powerful and they can handle things that maybe run-of-the-mill traditional statistical tools cannot. And there's a great example of that, which is there's this Datasaurus. So I'm going to show this example where we're going to have lots of different data sets, right, that all have the same summary statistics. So mean and standard deviation and correlation. So Y mean and standard deviation, X mean and standard deviation, even though they're very different. And one of them is actually a dinosaur, right? But you see these values are not really changing. And so we have to visualize this, and we wanted to, let's say cluster that dinosaur, we'd have to use something like dbScan, right? So this is Datasaurus. It's basically, an updated version of, I think it was like Anscombe's Quartet, which were 4 data sets that had, similar summary statistics for both the X and Y variables. Okay. All right. Okay, so that's great. I see some other things in the chat that are really, really wonderful. Stephanie, thanks so much for all that insight. That was really, really great. I think you said it better than I could. Right? I also see here that, so these algorithms probably work better when things are kind of densely grouped. Okay, and I think it's especially true for dbScan, that there needs to be a certain level of density, or else it'll kind of give up, right? And kind of, stop adding to a current cluster that it's building. Okay, all right. But it can handle irregular shapes, whereas k-means kind of requires clusters to be circular or spherical, or to kind of have this type of a regular shape. All right. The last point is k-means requires us to say how many clusters there should be at the beginning, whereas dbScan does not. dbScan will work through the data and create a certain number of clusters. The number of clusters depends on the data, and we don't have to provide that input. Okay, so there are 2 inputs for dbScan that we can change, right? But I'm not going to go over those right now. All right. What I'm going to do is I'm going to go back to the materials, unless someone else had some other thoughts on these 2 algorithms, or some other observations, or maybe a question. All right. So how does each algorithm work? Right. With k-means, we assign centroids, and then we update those centroids. We move the centroids to match. Okay. So k-means is actually fast. dbScan can also be fairly fast, but I think it's not as fast as k-means. Right? Even though we had to kind of manually click, that took a long time. But you could see how k-means can arrive at a solution pretty quickly, right? So here, if I restart, I'm going to pick the smiley face again. I'm going to do, maybe this time I'll do 4 just for fun. And then, you know, so after a few updates, we're pretty much already have an answer. Okay, maybe then it's being fine-tuned, but after some time it's converged, and it doesn't matter how many times I click this. This is the final answer. Okay, so it can be pretty quick. Whereas if we do DB scan again, you'll see as it's moving through, right?
Go ahead, I'm listening.
It has to go through a certain number of points. Kind of, it finishes a cluster, and then it moves on to the next one. Okay. All right. So k-means is probably going to be, that's another reason why it's the default choice or smart default, because it's going to be very fast. Okay, it's quick, it's robust, it works with, works really well. Right? Okay, so k-means you assign the centroids and then you update them as you work towards convergence. Convergence is where the algorithm says, okay, I'm like making small changes, but it doesn't seem to make any difference. I think I've arrived at the final answer. Okay. All right, so here's another question. So k-means, and actually all of these algorithms really only work with numerical values. So anything that we're putting into scikit-learn has to be numeric. And we can take categorical data and replace it with numbers. Okay, so we can basically do some data engineering or some data wrangling to get it into numeric form so that we can put it into scikit-learn. Okay, so that's what we're going to do. What we're going to be doing very soon. All right. So what about limitations? DB scan requires a certain kind of level of density, but it can handle irregular shapes. Whereas k-means kind of requires shapes to be regular, and it's best if clusters are kind of spherical or round, and that kind of in all of their dimensions, however many dimensions they have, that they're normal. The data are kind of normally distributed across all of the dimensions. And that's what k-means works best. And then, of course, it's easier when clusters are compact and then distinct from other clusters. Okay, so this is, I think, a nice exercise to kind of compare and contrast these two algorithms. I'll talk a little bit about distance metrics, but the main distance metric that we care about is actually Euclidean distance. And Euclidean distance is kind of in contrast to Manhattan distance. Manhattan distance, also called city block distance, right? And so what we have here is city block distance. You can't go diagonal. You can only go in kind of perpendicular directions. All right. So here in this example, we're going to move one direction, then the other, in kind of 90-degree angles, right? And so we sum up those distances, and that's our Manhattan distance. Okay. With Euclidean distance, we can just cut straight across. So we don't have to, imagine if we could kind of go through buildings rather than having to walk down the streets. Right? So maybe if there were a tunnel underground that we could just kind of walk from point A to point B, that would be the Euclidean distance. If you were walking on the street, that would be the Manhattan distance. Okay? And so there's a generalization of Euclidean and Manhattan distance, and that's called Minkowski distance. Okay. Here with Manhattan distance, what we would have is just this part that I highlighted. Okay. With Euclidean distance, we also are basically taking here to the power of 1/2. Okay. So we're going to be basically getting the square root. Right. Okay. So this is Euclidean distance. That's the main distance metric that we're going to use. Okay. So to look at these different distance metrics, we'll import some things. So we've got NumPy for numerical processing. We have Seaborn for visualization. We have Pandas for data wrangling, matplotlib also for visualization, and then SciPy is just going to be used for some distance measurements, and then scikit-learn as well, some pairwise distances, okay? So here I have some code, and I'm providing 2 data points in this NumPy array, all right? So the first data point, x equals 1, and then y equals 5, all right? For the second data point, this green one, x equals 2, and y equals 4, all right? So you can think about it. So what would be the Euclidean distance between these 2 points? Right. So the Euclidean distance is going to be basically a straight line going across. That wasn't really straight. Let's see if I can. Maybe I need to pick a better tool. Okay. My ability to draw a straight line is very bad, as you can see. All right. So that's going to be the Euclidean distance. What about the Manhattan or city block distance? There we're going to go, we can only go in right angles. So we're going to go from 5 to 4. That's going to be 1. And then we're going to go across here. So in red, I have the Manhattan distance. In cyan, I have the Euclidean distance. Okay. All right. Let's move on. This is just a quick example. All right, so here this pairwise distances. We can set the metric to be Euclidean, and we'll get out the Euclidean distance, okay? So this Euclidean distance, let me go back here and write it out. So the Euclidean distance is going to be 1. Well, let's say 1.42, right? Okay. And then the Manhattan distance is going to be 2. So let me get my arrows back. Okay, so this is going to be Manhattan distance. Okay. And then the Euclidean distance, I'm going to pick I'll pick a different color this time. I'll pick blue this time. I think it's going to show up better. Okay. And then here, it's going to be 1.142, which is really the same thing as saying, the square root of 2, right? And then our Manhattan distance, that's going to be 2. Okay, because we've got basically 4 to 5 is 1, and then 1 to 2 is 1. Okay, so this 1.42, that's going to be basically the square root of 2. So that's the hypotenuse to the triangle that we were drawing before. Okay. All right, so there are plenty of other metrics. And so here there are some examples. Euclidean, Manhattan, we talked about cosine similarity, or cosine distance, right? Correlation. These are other examples, okay? There are also distance metrics for binary data, okay, but you don't have to worry too much about those. In the actual notebook, all right, so I'm going to switch to, or try to find, here's the notebook. In the actual notebook, there's kind of a summary of all these different types of distance metrics, okay? The main one that we're going to focus on is Euclidean distance. And as a way of kind of understanding the difference between Euclidean and Manhattan distance, okay, I brought up, Manhattan distance just to contrast it to Euclidean distance, okay? So there are plenty of other examples, we don't have to worry about those. I didn't even include them in the slides. Okay. So for binary data, we might have different distance metrics, like for example, Jacquard or Hamming distance. In this example here, I'm using a function called makeBlobs from scikit-learn, where we're creating a synthetic data set. And then I can plot that synthetic data set, right, showing this kind of a heat map. And so this is kind of just random data. Right? So we can use something like this to generate random data for examples. Okay, so here we'll have 30 rows in our data set. We're going to have 4 clusters, and we're going to have 10 columns. Okay. So that's synthetic data. We can also look at, kind of these pairwise distances in the form of a plot. We can look at it in the form of a histogram. So in a histogram, we have the actual values. These are the distances on the x-axis. And then how often those values show up in our data on the y-axis. Okay. So this is looking at Euclidean distances in this synthetic data set that we created on the previous slide. Okay. So there are lots of different clustering algorithms that are included in scikit-learn. All right. So we talked about, dbScan. We also talked about k-means. K-means not shown here. Other ones that we'll get to will be agglomerative clustering. Okay. And then I'll also discuss mean shift, but we won't kind of implement that one. Okay. And then you can look at how these different algorithms behave. So going back to Stephanie's question from before, is if you're familiar with these algorithms and you also know what your data look like, you can maybe then make an educated guess about which algorithm is going to work best for your data, for your specific situation. All right. But, generally, the workflow will be try k-means, look at the results with k-means, and then decide whether k-means is fine or you need to move to something else. Okay. All right. So there's a question in the chat. Okay, so I'm gonna kind of read through it. So dbScan has an advantage that it's easier to use. Okay. One of the general is that each cluster should have a similar feature density. Okay. Okay. So the question is, when we find that k-means algorithm is inferior, but the quadratic variation algorithm would have similar results to those produced by dbScan, do we need to set up new data points to compare, or will conflicts of interest pose more problems for us in the long run? So with clustering, generally, we're working with all of the data. If we're able to obtain more data, then we can add it in. But it's more cut and dry to just compare these algorithms. We'll have some kind of metric. We'll talk about 2 metrics later on for how to assess clustering, and we would basically choose the right algorithm based off of those metrics. Okay. Now, there's another really important point with dbScan, is that it can give up on certain points. All right, so it won't necessarily cluster every single data point. Okay, so you might look here in this kind of middle example for dbScan, some of the points are black. That's where no cluster was assigned because essentially it's too sparse for dbScan to have kind of made its way over there. All right. And we saw something like that in those kind of density bars data set, where dbScan kind of gave up and didn't assign anything. So if that's something that we don't want to happen, we absolutely want to assign a cluster label to every single observation, then dbScan might not be the right choice. Okay, it works great for this, kind of nested circle, concentric circle data set, but it might not be the right choice for other data sets. Okay, where, if we don't want to have the situation where some of the observations are not assigned to a cluster, then dbScan might not be the right choice. Okay? We might want to choose, something else. Okay. Great. So moving on, there are going to be different kind of families of clustering algorithms. So we'll talk about agglomerative clustering, which we can also just call hierarchical clustering. We talked about k-means, and we talked about dbScan. So maybe, in the future, there'll be some other algorithms. I don't know if we'll be able to get to this. I was thinking we might be able to do some others, but the ones I want to focus on, k-means, dbScan, and then hierarchical clustering. So we at least have kind of these three families taken care of. And then I'll also mention mean shift. Okay. So first of all, k-means, to kind of explain a little bit about what we were looking at before. All right, we have our centroids, and our centroids are going to dictate where the clusters are. All right, and we want our centroids to be in the middle of the clusters. Okay, so that's why we're going to be updating the centroid locations to try to move them towards the center of the clusters. And so this is going to be iterative, step by step. We're going to be improving until we hit convergence, or maybe if there's a stopping condition that was included. All right. Okay. So here the stars show the centroids, and then, in the circles, we've got our clusters. And then these lines, black lines, show distances from the centroid. Okay. And here we've got 3 clusters. So for this data set, k-means looks like it's going to work just fine. Okay. Here's a, k-means clustering flashcard. So actually, the link is for this one, but these flashcards by Chris Albin, and he has these on his site. Okay, and here's basically the step by step in Chris's words of how k-means clustering works. We've got k-center points that are kind of created randomly. We have observations that are assigned to the nearest centroid or center point. Okay, and then we adjust the centroids, and we repeat 2 and 3 until we hit convergence. So that means no observation changes membership. Okay, or some kind of stopping condition is reached. Maybe we set a hard stop, a hard limit on the number of iterations that we can do, right? Okay, but I think this is a very good summary. That's why I included it here. Okay, and here's kind of k-means in action in a GIF or GIF, depending on how you pronounce it, right? These X's are the centroids, and you can see the centroids being updated as we work towards convergence, okay? All right, so there's a question in the chat. All right, so if that is the case, dbScan ignoring certain data points, would we reanalyze those data points to determine why they're not representative, or conclude that dbScan is not the right? You could do both. You could determine, or you could conclude that dbScan is not the right tool for the job, or you could try to adjust the settings in order to capture more of those points that are considered, outliers and are not assigned cluster labels. Or, so you could tune the algorithm to work better for the given data set, or you could switch to another algorithm and just say, it's not the right tool, we'll try something else. So you could do both, right? And then looking at the visualization, you might be able to say, if we change this parameter that we're providing to dbScan, we might be able to adjust the results in a way that's satisfactory, right? And then if not, we need to switch to a different algorithm, okay? All right. Okay, so agglomerative clustering is bottom up. That's exactly right. All right, and so we actually have individual observations and then we connect those. Would you say that gene expression data might also exhibit this hierarchical quality? Okay, I would say yes. You can certainly have families of genes, right? So that's true. An advantage of agglomerative clustering is they can produce an ordering of objects which may be informative for data display. I think yes, definitely. Showing a dendrogram, so basically a tree chart of your hierarchical clustering, that's a major advantage of agglomerative clustering. Okay. To fully exploit the unlabeled data, we can we propose Laplacian regularized metric learning technique, which leverages the distribution of unlabeled data and ensures the smoothness of metric learning through a regularization framework to resolve the optimization problem efficiently? So that's a really great question. And I think certainly you can do that. So there are plenty of kind of things that you can do in addition to the clustering to try to improve the results. So one thing that we'll do in the exercises is to standardize the data, to normalize the data. That's something that we can do. You can also have, kind of use any other kind of additional techniques in kind of a pipeline. Right? So certainly that's definitely possible. And thanks for that question. All right. Okay, so this is an example where we've got two centroids and it looks like two clusters, and I think this works really well. So we're going to move the centroids until it doesn't make any difference. Moving the slight variations, no cluster labels are changing. Then at that point, the algorithm has converged, okay? So here's an example with 3 centroids. All right. So these X's, again, are the centroids, and they're moving. They're being updated as we go through the steps. So each iteration is a step. All right. We first choose the centroids randomly, then we assign clusters, and then we adjust and repeat until convergence, or maybe there's a certain max number of iterations before we have to say we're done. Okay. And so here we've got 3, I would say, clear clusters and 3 centroids. So this is working, working well. So, k-means is perfectly fine for this data set. So k-means clustering, there's kind of from our model object that we get from scikit-learn, we can get something called inertia, which is basically going to be, the sum of squared distances of samples to their cluster center. So this cluster center, that's the centroid. All right. And by the way, the k in k-means, that's the number of clusters. Okay. All right. So on its own, this inertia, or sum of squared distances, doesn't really mean anything. The actual number doesn't mean anything, but we'll want to use it to compare across different numbers of clusters to see which number of clusters is best. Okay? So we can use this. This is one of those metrics that we can use for assessment. Okay. Okay. So moving on to other types of clustering methods. So we'll have mean shift. The reason why I bring up mean shift is another one of these, clustering algorithms like dbScan, where you don't have to say, how many numbers of clusters, okay, you want at the beginning. Okay. But you will have to provide a parameter called R. Okay. And then you can see how, as you move through the iterations, you're eventually going to find the centers. Okay. And then from those centers, you're going to kind of go out a certain distance. All right. Kind of what we start with is we start with a grid at the beginning. And the way that we can kind of explain this is, imagine you're in a foggy field, and you see only people who are kind of nearest to you, and you move towards the highest number of people that you can see, okay? And so you see how these points are kind of converging, like maybe these people are kind of moving towards each other until we find these centers, okay? All right, and that's essentially, I think I have this, or I should have this in the notebook. Looks like it's not showing up in the slides. So we've got k-means, and then here mean shift. I forgot to turn this into a slide, but it's exactly right. You're in a foggy field with 100 people standing on it, and they're equidistant. You can only see a short distance, and then with each iteration, you look around and you step in the direction where you see the most people. Okay. All right. So, as time goes on, you move towards larger and larger crowds. Okay. The end result is clusters of people around the field. Okay. So this is again Chris Albin, kind of giving us a way to understand mean shift. Okay. And so after it converges, we have our centers. We look out a certain distance from those to define our kind of the boundaries for our clusters. Okay, and that's set by this R parameter. Right? Now here in this data set, we've got some clusters that are fairly dense, right, and kind of tight. Another one that's fairly sparse. And you can see how mean shift around the edges isn't doing super well. All right. Okay, so here's a question. Does this mean theoretically multiple groups would naturally form, not one group in the center of the field? Exactly. So that's what we're, based on the data, we'll have these people kind of moving towards their nearest cluster as center, right? And that's what we're seeing. So basically these clusters are forming naturally, if you will. So we don't have to specify the number of clusters beforehand. That's exactly right. Okay. All right, so we already talked about dbScan, and this is really familiar. Probably you can see this example, or you recognize this example. And so this is an example where, dbScan works well, but in this specific one, there are going to be some points which are not addressed. Okay, so they're not assigned cluster labels. So that's one very important thing about dbScan. So dbScan, we also don't have to specify the number of clusters beforehand. All right. So here's the machine learning flashcard for dbScan, again from Chris Albin. All right. And then I'm not going to talk about specifically what dbScan does, but this is kind of provided for your reference. All right. So I think this is the last one that I'm going to talk about is hierarchical clustering. And so it's agglomerative. What we do is we start with each observation. So here we've got P0 through 6. Each starts out in its own cluster. And then over time, we're combining those clusters until we get to the point where we've combined all of the observations into a single cluster. And that up here, that's called the root. Okay, so it's, the root of the tree, right? This tree is kind of growing upside down, right? The root contains all of the observations, whereas the leaves, right? Those are these kind of terminal nodes at the end. They each contain one observation. So we start with the leaves, with each observation being in one cluster, in its own cluster by itself, and we combine the closest observations until eventually we get to the point where we get to the root node, and all the observations are in one cluster. So it kind of works backwards from what we might want to think. It starts at the leaves and then goes to the root. And also this is visualized kind of upside down, where the leaves are at the bottom, the root is at the top. So this is working the opposite way of how we might envision a tree will work. All right. But I think it was, I don't want to get it wrong. I think it was David who brought this up. Is that right? Because there have been lots of questions. You brought it up that it was, correct me if I'm wrong. Okay, yes, David, you said, an advantage of agglomerative clustering is that we can plot it as this dendrogram or this tree chart. Okay. And so we're joining together observations based off of some kind of distance metric, and Euclidean is, the main example that we can just focus on. We're going to say we're going to use Euclidean distance. Okay, so that's the default for scikit-learn, right? Now, once we have these final results, then we can decide, based off of this, how many clusters do we want? Where do we draw the line? Okay, so here it's showing Euclidean distance, right? Where do we draw the line? At 5 clusters, right? Maybe at 3 clusters, or at 2 clusters, right? So where do we slice this, right? What's going to be the most meaningful or useful for us? And this visualization also helps us to understand our hierarchical clustering results. Right? So you have agglomerative clustering. All observations start as their own cluster. So those are the leaves of the tree or the terminal nodes. And then clusters are brought together. So usually I would say Euclidean distance is the most common. Okay, so they're merged. Okay, and this is repeated until some endpoint is reached. And so that some endpoint is going to be, in that example, when we reach the root node where all of the observations are now in one cluster. Okay, so now we're at the point where we're going to get started with the practical component. And for this, we're going to be working with a data set called the iris data set. Okay, so the iris data set, this is, oh, sorry, was there a question? I thought I heard someone on mute. All right, maybe not. All right, so iris data set, it's using data on flowers. So we're going to have measurements of 2 anatomical features of flowers, petals and sepals, right? And so this iris flower is, we can see what these 2 anatomical features look like. And in our data set, we're going to have the length and the width of the petals and the sepals. All right. So here what we're doing is we're going to have some imports. Some of these imports we saw before. It's a little redundant, but that's okay. And then we're going to have create a data frame, a pandas data frame, where we're going to get out the data that we use for prediction and the target, okay, from our iris data set that we're loading in here. Okay. We provide the column names. This is a Python tuple. We provide our column names here. So this is a useful data frame. We've got everything. We can pull out the true labels. So this is iris true labels. And then from our data set, we're going to drop the labels. So we're going to work with, unlabeled data. Okay, so in our iris 4D, we're going to remove this species column. That column, those are the true labels. All right, for clustering, we're not working with those. Right? Okay, and then we're also going to create this another iris data set. And that one is just, we're going to drop 2 of the columns. So this iris data set is going to be iris 2D. Okay? So we'll look at some examples. All right. From scikit-learn.cluster, we're going to import k-means. And then we're going to set up our k-means algorithm. And a lot of these things that are provided here, these are the defaults. But I just kind of list these out. All right. So we're going to say, you know, how are we going to get started? We're going to use this k-means plus algorithm, right? How many starts are we going to have before we kind of decide, you know, to kind of, that we're not going to be biasing the results just by randomly starting in the wrong place, right? And then how many iterations do we go up to before we call it quits, right? And then random state is for reproducibility, so that as long as this is set, right, because where we're starting is random, but as long as this is set, we'll always have the same results. So our code is going to be reproducible. All right. Okay. So we've got here our model. So we import, then we instantiate the model, and then we can fit the model and also generate our predictions, which are the cluster labels. Okay. So here we've got the cluster labels. And the cluster labels, this is going to be, you know, because we have two clusters, it's going to be binary. So it's going to be zeros and ones. Okay. Then we're going to create this function. We're going to use this function quite a lot. It's going to be plot k-means, where we're going to pass in the data, pass in the cluster labels, specify the model, and then say how many clusters there were. And this function is going to basically handle the plotting for us. Okay, so we don't really have to worry too much about the code that's in this function. We're just going to use this function to visualize our clustering results. Okay. So here we go. So we instantiate our model right here. Then we fit the model. And then we're going to create our predictions. So here, this predict, now it's in 2 steps. And then we're going to pass in the original data, the labels, the model, and then the number of clusters to plot k-means to create this nice plot. Okay. So the red circles, those are the centroids. Okay. And we've got our clusters labeled as blue and orange. Okay. So when I look at this, I say, okay, this looks, you know, very reasonable to me. We're kind of drawing a line down the middle and splitting these data points, the observations, into 2 groups. Okay. All right. So this is where we have iris. Remember, that's 2-dimensional. So we can look at what would it look like if we had 4 dimensions. And now we're looking at all 4 dimensions provided in the data set. So that's petal length and width, and then sepal length and width. All right, so we instantiate the model. Then we fit the model. And we create our predictions. So we have our cluster labels here. Okay. And then we pass all the things that are needed to this plot k-means function to plot our new clusters. Okay, so we're still saying that we want 2 clusters. All right, but now you can see how things have changed. We've got a different, you know, split. It's not kind of right down here in the middle. We're kind of drawing a diagonal line, in a sense, right? And our centroids have moved, right? So the data that we provide for as features will change how you know, where our centroids end up, and our centroids determine where the clusters are. All right, so here's a more complex example where we're saying we want 3 clusters, right? And I'm using the 4-dimensional data set, and I'm saying we want to show 3 clusters. And so we've got 3 centroids, all right, these red circles, and we've got 3 clusters, right? Blue, orange, and green. Now you may notice that these clusters aren't very clean. And so this data set, well, at least, you know, one of them is kind of distinct, but the other 2 are overlapping. And that's kind of the point, to show, you know, not just clean examples, but ones where there's going to be some, you know, some, let's say maybe like a fuzzy area between these clusters where we're not sure what the assignment should be. Okay, so this is kind of an example of clustering task, which is a little bit more difficult than maybe ones we've seen. Okay, up until now, right? Okay, and then here, so why is this, you know, it looks like there's some mixing happening here. Well, what we're looking at is we're looking at just 2 dimensions of the 4. All right, so how could we look at 4 dimensions on a single plot? Well, for that, we could use principal component analysis, or PCA. That's a dimensionality reduction technique. And so that we're going to do actually at the very end, right? All right, so next up, what we're going to talk about is evaluation of clustering. And there are going to be several metrics that I talk about. Some of those metrics will require knowledge of kind of the true labels or the ground truth. And if we don't have knowledge of the ground truth, then these metrics are not going to be useful for us. Okay? There are 2 metrics which are called, you know, silhouette coefficient, and then the elbow method can actually use the silhouette coefficient or that inertia metric, because that's the sum of square distances within a cluster. So we're going to use some kind of metric. We're going to plot it out, and we're going to look for an inflection point. So that's the elbow method, okay, which I believe was already discussed earlier on in the course. Okay, so these are the 2 metrics that we kind of focus on because they're the most useful, because we don't have to know what the true cluster labels should be. Okay. The other ones, this would be for looking at a clustering method and trying to see how it really compares against the ground truth, those known cluster labels. All right. So using these metrics, we can find the optimal number of clusters, and then also we can compare different clustering methods. Okay. So which clustering method to choose, and then also how to set the parameters for each clustering method. All right, so for K, the main parameter, so for K-means, the main parameter is K, the number of clusters, okay? For mean shift, it's R, or that radius. And for dB scan, there are going to be 2. Okay? So it's the epsilon and then the minimum number of points. Okay? So using these evaluation metrics or assessment metrics, we can kind of answer all of these questions, right? So how do we determine whether our algorithm is successful or not? How do we know how to set the optimal number of clusters for k-means? And then how do we pick the right clustering method? And then also how do we tune that clustering method by providing it the correct values of parameters? So all of this we do with model assessment, okay? And so here, this is, you know, let's say we already know these correct labels. We're going to be able to use some of these metrics that require ground truth, like this adjusted RAND score, also called adjusted RAND index. Okay. And so here, you know, with adjusted RAND index, it's bounded between -1 and 1. Okay. 0 basically means that it's kind of random. 1 is perfect clustering, okay? And then below 0 means that something wrong is happening, okay? We're getting worse, I guess, than random clustering, right? Okay, so we can apply this to our actual data set. So we have our true labels and the cluster assignments. So this is the output of our clustering. Okay? And then we'll look, and so here, according to the adjusted RAND index, where you know, we're somewhere between random and perfect. Okay, all right. So that's the adjusted RAND index. There's also this mutual info score. Okay, So really has this kind of same range, okay? So bound between -1 and 1. 1 is perfect, 0 is random, less than 0 is bad, okay? So here this, this is the result of this adjusted mutual info score, okay? Then we can look at, this kind of homogeneity, completeness versus measure. Okay. So this will give us, the homogeneity. So it's going to say each cluster contains only members of a single class. Completeness, right? All members of a given class are assigned to the same cluster. Okay. And then, we'll get kind of multiple things out from this method. All right, I'm going to switch to the notebook really quick and show you when you're looking at all of these things. I think I'm kind of zoomed in pretty far. Hopefully it's not too bad. I'm going to move to this part of the code. All right, and I'm going to just import here metrics. So here I'm importing metrics. Turn some of these things off. Okay. And so the reason why I wanted to import metrics is so that then I can do Shift Tab, maybe Shift Tab twice, and I can bring up the documentation for each of these methods. And you can do this with anything that's in Scikit or inside of Jupyter, right? So Shift Tab to bring up the documentation. All right, so here this adjusted mutual info score. You can also bring up the documentation for that. All right, and then down here for this homogeneity, completeness versus measure. Okay. And then another thing that we can do is that when we have metrics and we press dot and then we press tab, we should have then a list of all of the different things that we can get. Okay, so this homogeneity, completeness, okay, versus measure. All right, so here's the documentation for that. Okay, so after the dot, I press tab to see what's available. And then once I have what I want, I do Shift Tab to look at the documentation. Okay, so we get out the homogeneity, completeness, and V-measure scores all at once. So we get out these 3 different values. Okay. So moving on, so how do we determine the right number of clusters? Okay, so we're going to look for an inflection point. This is the elbow method. So I think it was kind of discussed before. But we're going to have a plot, an elbow plot, where we say, okay, we're looking for the inflection point. And where we see that, okay, adding an additional clusters stops really helping us, right? Because the benefit, right, this kind of like sum of squared distances, this is the inertia. We're literally pulling out inertia from our k-means model object here, our k-means instance. All right. So here, this is inertia. The lower, the better. But at some point, it starts to plateau. And then, really, I think past 3 clusters, it might not make much sense. We're not really gaining much in terms of lowering the inertia by adding on additional clusters. Okay, so depending on who you ask, different people might put different have different answers here. But for me, if I look at this where I kind of see the elbow would be here at 3, right? Others might want to put it somewhere else. I would say, 3 clusters based off the elbow method here this would be the right answer. Okay. And so this is subjective. You know, depending on who you talk to, you might have different answers. Okay, so you look here, the elbow method, where do we see this inflection point? That's what we want. The reason for this is because this inertia measure, it will keep decreasing, it'll keep getting better as we add on more clusters. So it'll always be getting better and better. So we need to have some other kind of criteria to say, when do we stop? Well, we're going to stop at the inflection point where it stops making such a huge difference. Okay, where the gains of adding more clusters really start to deplete. It's like the law of diminishing returns in economics. Okay. All right, so there's another question. Maybe what I'll do is I'll save this question. It's another question about dbScan. I'll save that question for the end. All right. So here's another example where I'm instantiating the model. Here I'm using fit and predict all at once to create my cluster labels. And then I'm plotting this result. Okay. So here when I look at this, this looks pretty good, right? So I've got 3 clusters. And that actually matches what I know about this data set, that there are actually 3 unique species. Okay. So maybe I'll show that really quick. I'll have to scroll to the top of this iris data set. So I'll load in the data set. And then I have here this iris true labels. Okay, iris true labels. And I can look at these. And they're going to be, 3 values there, 0, 1, and 2. And the best way that I can look at that is actually right after loading in iris, I can look at iris, and then in square brackets and in quotes, look at the target names. Okay, so there are 3 target names. These are 3 species of iris flower: Iris setosa, Iris versicolor, and Iris virginica. All right, so I know that there are 3 actual labels. And so when I look at this, this also matches my, my knowledge of this data set. Okay. All right, so we can kind of create, collect some of these metrics along the way. So inertias, adjusted rand indices. All right. And so here, this adjusted rand score is adjusted rand index. It's the same thing. So we collect that in ARIs. We collect the Ks as we iterate through different Ks. And then we can also collect inertias. All right. So then we can plot all of these things. And we'll see here, so a K of 1 has a high inertia, right? A low ARI. Right? And then looking at these 2, I think there's one kind of clear winner, right? Which is here 3, which has the highest ARI. And then I would say a moderately high inertia. So we want the inertia to be as small as possible, and we want the ARI to be as large as possible. So here we're using 2 metrics to try to figure out what is the correct number of clusters. Okay, so this is different than the elbow method, but it also uses inertia or sum of square distances within, right, each cluster to determine what the right number of clusters is. Okay. All right, so the last thing that we're going to talk about today is the silhouette coefficient. Okay. So the equation for the silhouette coefficient is rather simple, but for it to be simple, we have to understand what A and B mean, okay? So A is the mean distance between a given observation and then, all other observations in that same cluster. Here it says class, but it's, cluster. Okay? And then B is the mean distance between an observation and then all other points in the nearest cluster. Okay, so this would be within a single cluster, within the same cluster as that observation, and then B is distance to all the observations in the nearest cluster, whatever the nearest cluster is. Okay, so let's call A within and B nearest. Okay, so we take nearest minus within, right? And then we divide by whichever is greater. So either within or nearest. Okay? And this is how we calculated a silhouette coefficient. Because the silhouette coefficient is in a sense kind of normalized to something, the silhouette coefficient is, we don't have to worry about having too many clusters, right? We can just pick whatever the largest silhouette coefficient that we can find is, right? So for the silhouette coefficient, maybe we wouldn't really use, the elbow method per se, but we can still plot it. There we won't find the inflection point. Rather, what we're going to look for is, the highest value, okay, for the silhouette coefficient. Okay, so here there's a lot of code. This is to plot the silhouette coefficient. Again, it's a function. You don't have to worry about what's going on in the function. The function is just going to give us the plots that we want. Okay. All right. So here we have, plot silhouette scores for two clusters. So we've got two clusters, and this dashed line, that's going to be essentially the average silhouette score. Okay. And then these kind of waterfalls, those are going to be the silhouette coefficients for every single observation in each cluster. So we've got cluster 0 and cluster 1. Okay? And then we can look at all of the silhouette scores for kind of every observation, cascading down from the highest score to the lowest score within a given cluster. All right. So this is for two clusters. Right. Next up is three clusters. All right. So we can look kind of, our silhouette score here was below 0.5. Now our silhouette score is above 0.6. So that's an improvement. All right. And the silhouette scores for cluster 0 and 2 are higher than for cluster 1. All right. Cluster 1 also has more observations than 2 and 0. All right, so these are things that we can pick out from this kind of silhouette plot. Okay, so here, this is, similar, but we just have in a different order. But the overall score is the same. Okay, so the dashed line, again, that's mean silhouette score overall for the entire, for this entire kind of clustering run with 3 clusters. All right. So -1 would be really bad. 1 is going to be perfect. 0 means that, we basically have overlapping clusters. There's not really, it's not really helpful clustering. And so the silhouette coefficient, right, is going to tell us, whether we have kind of dense clusters. It may not work well in other cases. All right. But here we're seeing that our clustering is actually fairly good, right? So 1 would be perfect, 0 is random. Okay. And so the silhouette coefficient can also tell us how many clusters we want overall. We may want to look at, here the silhouette coefficient across, multiple numbers of clusters, and then we could pick the highest. All right. So based off of ARI, which is adjusted rand index, and also the elbow method, the right number of clusters would be 3. According to the silhouette coefficient method, the right number of clusters may actually be 2, right? And then you can see as we add on clusters, right, our silhouette coefficient actually goes down. And so that's why we can just pick the highest value rather than worrying about, oh, are we having too many clusters? With the elbow method, right, with inertia, that's a metric that will always increase when we add on more clusters, but that's not the case with the silhouette coefficient. Okay, so I think that's rather useful. All right. So here again, we've got a function just to calculate the silhouette coefficient, right? And then we're going to go ahead and plot those calculated scores. All right. All right. So that's everything that I had planned for today. All right. So next up would be, understanding our clusters. The clusters that we get out, we'll use decision trees and then also principal components analysis to visualize and to understand our clusters. That's coming up for tomorrow. All right. For today, what I wanted to do is, we've got 3 minutes left. So I wanted to maybe do kind of a higher level overview of where we're at right now. So right now we've covered a lot of material. In the notebook, we're here, kind of understanding clusters, decision tree. So right before we get to 28, so we just finished 27, all right? And at the bottom, there are going to be exercises, all right? And now these exercises, really I would hope that you would be able to do most of these exercises, right? The last few exercises are for those people who are asking, extremely detailed questions. They're supposed to be very, very challenging, right? So if you cannot, and certainly this last one I think is tough. Here, this one as well. Let's say let's say maybe 5, 6, and 7. Those are kind of considered. I would consider those bonuses. Certainly 7, consider that a bonus, right? But 1, 2, 3, and 4, I believe you should be able to complete based off of what we've done today, okay? So what I've done is I've shared, the answers to the TAs with the TAs, so they should be able to help you to complete these exercises if you get stuck. But there's also plenty of kind of descriptions here in these exercises to help you get started. Okay. I would encourage you also to work in groups on these exercises because I think it's always more fun to kind of work on things together. All right. I'm going to answer some of the questions that popped up in the chat now. If you have more questions about, the course or anything that I covered today, please feel free to write in the chat. Okay. All right. So to clarify, you mentioned that more clusters can, so the higher the number of clusters, the better the inertia. So the lower the inertia, right? As you add on clusters, inertia will continue to fall, even if it's just a tiny, tiny, tiny amount, right? At some point, you're going to say, well, it's not really worth it, right? That's why we want that inflection point. When the return on the investment starts dropping, right, we'll want to stop investing, right? That's kind of the rationale, right? And then certainly you can have overlapping clusters, but there's a question of how does the algorithm handle that, right? Generally, you have to have kind of distinct borders for the clusters, okay? So there's some place where you have to kind of draw a line. It also depends on how you're looking at these clusters. Usually as a two-dimensional plot, what are you plotting? Is it 2 variables? Or maybe using principal component analysis, two principal components, right? But overlapping clusters, certainly that can happen. Right? Okay, so to clarify, what the methods we learned today decide the cluster number differently. Yes, so k-means, for k-means, we decide the number of clusters. For mean shift and dbScan, those mean shift and dbScan decide the number of clusters for us. Hierarchical clustering, we also decide the number of clusters ourselves, okay? So just something really quick. If we have kind of hierarchical clustering kind of imported, and so here I have hierarchical clustering here, agglomerative clustering here. Okay, so I'm going to import that just so then I can show you the methods. But you see here I'm setting the number of clusters for agglomerative clustering. Okay, so if you see something like this, agglomerative clustering or k-means, you'll see that they have a parameter here that we can set. All right, so this n clusters, it's going to be the same thing for k-means. So agglomerative clustering and k-means, we set the number of clusters. And for mean shift and dbScan, we don't set the number of clusters. All right. Okay, excellent. Okay. I'm happy to stay and answer any other questions that anyone might have. But if you need to run, I understand. It is 1 p.m. now, right? Okay. See, there's some kind of more detailed questions. I'll go ahead and read these out loud so maybe we can understand them. But if you have any other questions, let me know. All right, so we learned that dbScan can reduce time complexity without increasing space complexity. It is interesting to me that while the dataset size increases, the clustering efficiency also increases, showing that the proposed algorithm can handle large data sets in an efficient manner. After pre-processing of the data and carefully selecting appropriate parameters, it is very possible for us to observe that both k-means and dbScan algorithms have strong intra-cluster cohesion and inter-cluster separation. It's great. With that shows that any of the algorithms can be used to cluster the data set. However, in terms of accuracy, k-means algorithm may perform better than dbScan, right? I guess it depends on the data set for sure. My question is, obtaining optimal cluster using the specified algorithm depends on the value of parameters chosen. Yes, that is true. Based on an analysis given both k-means and dbScan algorithms have strong intracluster. Yeah, so certainly it depends on those parameters that you provide. I would say, especially dbScan, if you set those wrong, you could get results that don't make any sense at all. But that's one of the things that we're doing when we're employing these methods. We're going to want to tune them. So for k-means, we pick the right number of clusters, and then for dbScan, we set the right epsilon and the right number, minimum number of points. Okay, and then it's going to depend from data set to data set which one is the better choice depending on the characteristics of the data set. Okay. All right, and then in terms of silhouette coefficient within the compound data set, is able to detect nested overlapped clusters. Say, but while no other method makes this separation, low class distribution of highly connected clusters means that for the time series segmentation task, hierarchical methods better isolate vector patterns, particularly succeeds in isolating them, considering that who can do more can do less. Who can do more can do less. My question to you is, if extracting spectral eigenvectors of a normalized Laplacian matrix derived from data similarity matrix followed by unsupervised k-means clustering. Okay, so k-means clustering is always unsupervised. K-means step would be replaced by some other clustering algorithm, is the objective still to offer the expert the possibility to define their own level of relevant expertise based on the best available number of clusters? And I think, certainly that is the case. So this is a really, so I'm getting a lot of questions which are being sent to me privately, so no one else can see them. And so, I've read them out loud, so I think you can maybe get the gist of them, and I'm going to just kind of respond to them very generally. And so again, this is another question where you can have, some kind of prior step. Maybe you're essentially running a pipeline, and we'll get to that tomorrow. So tomorrow, basically, what we're gonna have is, we're gonna have PCA. And you can have, let's say, for example, run PCA first, and then cluster based off of those principal components, right? And so, that would be an example of a pipeline. And then here with this question is, is the objective still to offer the expert the possibility to define their own level of relevant expertise based on the best available number of clusters? Okay, so I think, I'm thinking about this, the expert is going to be the user in this case, and then I think maybe, or is that the estimator? I think maybe I don't really understand the question. Yeah. So if you ask that question, maybe you can clarify in the chat or just unmute and let me know. Certainly, if you've got some kind of like an estimator, excellent. That's what I was thinking, right? Okay. So with k-means, you provide the number of clusters, but if you can certainly, in your pipeline, you can switch out another clustering method there. So basically, like you wrote there, with the k-means step could be replaced by some other type of partitioning algorithm, right? So certainly you can replace k-means with some other estimator, right? Some other clustering algorithm. And there, you won't have to specify the number of clusters. And indeed, the estimator will define the number of clusters, if it's mean shift or dbScan or another one of these types of algorithms, it'll define the clusters itself, right? So does that answer your question? Okay, great. Excellent. All right. So thanks for clarifying. Thanks for asking these, very detailed questions. Those questions are coming to me privately, so no one else can see them. And maybe if you're okay with it, maybe you could share those questions with everyone else. What I would suggest is maybe in the Slack channel, because these are like very detailed questions. Each one is like a book chapter. So if you're up for it, maybe copy those questions and share them in the Slack if you feel comfortable doing so. I think they're great questions. Okay. So because you're messaging me privately, I'm not naming names. I'm not saying anything. But if you feel comfortable sharing those, I would encourage you to do so that everyone can benefit from seeing those questions. And there's a lot of depth in those questions. Okay. So thanks so much for those. All right. Okay. All right. Awesome. Okay. Any other questions or comments or anything? It could be about, the course so far, this module specifically, anything else that anyone wants to discuss.
I think I'll bring the crowd. Oh, sorry. We have a student, so I'll let the student go ahead.
Okay.
Okay, so I'll jump in now. So I see you have an R Markdown for the clustering, and you have in there. So this is just for general information. We've been using Anaconda for IPython. I have been working with R Markdown. So when I saw this, I was like, okay, I'm not the only one. So what has your experience been? If you have a Python, run Anaconda. If you have R, use R Markdown, or combine both. Because here I see you have Python embedded in Markdown.
Yeah, so that's such a great question. It's more about the materials and the technical aspects of delivering the materials to everyone. All right. So inside of Codio, I just have the notebook and then this Python file. All right. The Python file is created from the Jupyter notebook, so it should have all of the content. It's just in a plain text format. Okay. But it's true that on GitHub, I do have an R Markdown file there. So, William, you're very perceptive, right? And the R Markdown file is also something that I generated automatically. And it's generated automatically using a tool called JupyText. And the reason why I do that is because I want to have these resources just kind of available in many different ways, right? So Jupyter notebooks are great, but maybe not everyone is going to love Jupyter notebooks. I think many people do, right? I would say probably the majority like Jupyter notebooks, right? But not everyone will. Some people may prefer R Markdown. It's another plain text format, right, where we can have all of everything here in a plain text format, so not a Jupyter notebook, which kind of requires rendering for us to view it, right, for it to look nice. Here we've got everything in plain text. And then in R Markdown, I can still run Python code using this type of delineation for a Python code block, right? So this is syntax for R Markdown. So this file that has extension RMD. All right. So you could run this. Probably the easiest way to run this would be inside of RStudio. And you can install RStudio via Anaconda, because you mentioned that you're using Anaconda. So if you open up Anaconda Navigator, there should be an option there to install RStudio via Anaconda. Okay. So this is just another way that I'm trying to make these materials accessible in a plain text format. If anyone is familiar with R and RStudio, this is going to be the easiest format for them. Of course, if everyone is used to Jupyter notebooks, then they can just use the Jupyter notebook. In addition to the Jupyter notebook, I provide the Python file, right? The Python file is going to have all the text, everything, and all the code as the notebook, but it's in a plain text format. What do I mean by plain text format? If we look at this Jupyter notebook, first of all, it may take a second to render. It looks really nice because everything's rendered really nicely. But if I wanted to look at the raw Jupyter notebook, it's going to look like a JavaScript object notation file, a JSON file. And that's going to be very hard to read, right? So if we want something that's plain text, then I would recommend either using this Python file, if you're more familiar with Python, or the RMD file if you're more familiar with R. But both of these work. And then if you don't want it in plain text, you can just use the Jupyter notebook, right? So I wanted to kind of make all these options available. And all of this is automated using that tool called JupyText.
Yeah, okay. Yeah, thanks a lot. In case it comes out, I mean, when I saw it, it made sense to me, but I want others to also have the benefit of hearing from you. So thanks a lot.
Yeah, yeah. And so one last maybe note about JupyText is when I'm making changes to the notebook, it saves these output files or these kind of associated files or paired files automatically. So I make a change in my Jupyter notebook, the IPyNB file, and then it updates the Python file and the R Markdown file for me automatically, right? With the slides, how I created the slides, it's also very simple, is I went to File and then Download as Reveal.js slides. Okay. So I would say like the ultimate source of truth is the Jupyter Notebook, but we also have a Python file and an R Markdown file if anyone kind of prefers those formats.
Jupyter comes with, I don't know how to look in Codio. I have Jupyter Lab, so I'm able to see that. But then in Codio, how would you, and you did this in Codio, right? So students should have the same view as you have. You did a file save as, right? Okay, cool.
Yeah. And so now I'm opening up Jupyter Lab in this location just to show how it looks in the Jupyter Lab interface. The Codio interface is going to be the classic notebook interface, right? So here I do download as Reveal.js slides, okay? But inside of Jupyter Lab, it's export notebook as Reveal.js slides. So here, if I go into module 4, locally it's a little bit more messy. I was kind of experimenting a little bit. And then I would do export notebook as Reveal.js slides to generate that slide deck, that HTML file. Yeah. But these are things that, no one has to, unless you want to recreate the slides, right, from the notebook, or you want to create your own slides from your own notebook, this is not something you have to worry about. Okay? All right. So if there are no further questions, what I'll do is I'll, hop off the call for today. And then tomorrow, we'll continue on. We'll talk about understanding our clustering results, so inference. And then we'll also look at the exercises.
Okay, any further questions for Martin? Okay, so if no further question, then Martin, we thank you so much for an excellent presentation on clustering. And then, as he said, we are going to have him again tomorrow.
Yeah.
A few housekeeping. The TA sessions will be on today from 4 to 5 p.m. and then also on Saturday morning, 9 to 10 a.m. and then Sunday evening, 5 to 6 p.m. All the times are Eastern Standard Times. So again, if today is your first time of joining us, thank you for coming. The recordings from Module 1 up to today and then tomorrow when Martin continues with it will be available in the Varsity GitHub. So you can go in there and then check for those past modules if today is your first time joining us. So again, thank you all for coming, and then make sure you sign in for those who need the credit. So you make sure you sign in. I believe the link is sent in Slack and then also here. So make sure you sign in so that you can get credit for your certificate. So again, thank you all for coming, and Martin, again, thank you, and then we'll see you all again tomorrow. Bye-bye.
Thanks so much, everyone. See you tomorrow. Bye.